Let's continue with our previous lesson, how to estimate performance from our simulation model. Okay, so we have talked about different types, two types of simulations. We can have a terminating simulation and a steady state simulation. And for each type of simulation, we may look at a tally statistic or a time persistence statistic. Okay, so we talk about the different ways to estimate tally statistic and the time persistence statistic. So basically, for the tally statistic, if we want to calculate the average, we just look at the traditional ways, the common way, the conventional way to compute the mean. But if it is a time persistence statistic, then we need to take the integration, all right, and take the time weighted mean. Okay, so when you ask the RANO to collect for you certain statistic which is not available in the default report, you have to choose correctly whether it is a tally type or a time persistent type, and so it can use the equation correctly. Okay, and this is for the point estimation. Let's say if we want to look at the confidence interval, want to estimate in the form of confidence interval, then we can use this formula, right, to calculate the confidence interval. Right. So the confidence interval has two information. Firstly, is the range of our estimation from where to where, right? Okay, we already have the point estimate, which is the average. Okay, and then we have the lower end and the upper end. We give the reader the range of our estimation. We call this confidence interval. All right, and from the average to the limit, it is a half width of the confidence interval. Okay, so the first information is the range of our estimation. The second one is how confident we are with this range. What is our confidence level of that range? So you can have a 95% confidence, or you are just 80% confidence, or you maybe just 70% confidence with this range, this given range. So the normal level that we usually choose is 95%. Okay, so when we say we are 95% confidence with this range, this means that when we plot the distribution, 95% of our observation will be within this confidence interval, will be within this range, 95% of our confidence. Okay, and when we say 80%, our confidence interval is from here to there. We mean that 80% of our observation is within that range. Okay, so when we state a confidence interval, there are two information. The first one is the width of the confidence interval, the range, the width of the range. And the second one is the level of our confidence, with 95%, 100%, 80%, and so on. All right, okay. All right, and then we go to details, how we should estimate the performance for the terminating simulation. Now, in the terminating simulation, you need to distinguish the within replication and the across replication data. Okay. Let me check. Okay. Let's say we look at certain output performance, like the time in system or the cycle time. Let me put it in presentation slide. Okay, so let's say we are interested in the average cycle time of any entity in our system. Okay, and we can collect the cycle time data from one replication. For one replication like this one, we can have many cycle time of all the entities that we observe in that particular replication. Okay, so all the data that we collect within one replication, we can still compute the average, all right, and the variance. Okay, and then when we run the simulation many times, many replication, R replication, then we can have the R average from each replication. This one we call across replication data. Okay, so last time I asked you why we need across replication data and why not use just the within replication data. All right, and I already give you the answer for this one, right? Okay, do you still remember the answer for this one? Why we need the across replication data? Why we need to run the our simulation many times and then take the average from many replication? Why don't we just run one replication and take the average from within replication? Do you still remember why? Okay, the case in here is that if you want to estimate the confidence interval, this is the half width. This is the half width of the confidence interval. If you want to estimate this one and use the equation that I gave you in the previous slide, okay, it's required that the data that we have should be independent. Okay, but if we look at within replication data, they are not independent, they are dependent. Okay, so the timing system of the 50 entity in our system would depend on the 49 entity. Okay, maybe and depends on the 48 and 47. There's a correlation between the entities within one replication. Okay, all right. So that's common sense, right? And because the data that we collect within one replication are correlated, so we cannot use the classic statistical equation to estimate the confidence width. All right. So in this case, this is the reason why we need to run many replication, because the across replication data the across replication data are independent. It seems that there's some I'm sorry, seems that there's some, okay. Okay, there's some internet drop in my computer. Sorry for the interruption. Do you still see the slide?
No, teacher.
Okay, let me share it again. The internet just falling. Give me a second. Okay, here we are. Okay, yes. All right. All right. It's okay now. All right. So the reason that we have to run our simulation many times is that we will have the across replication data, and the across replication data are independent. Okay, and then last time we mentioned about the central limit theorem. Okay, and it's proof that why we have the across replication data independent. Okay, but in short, they are independent, and so when we estimate the confidence interval from the across replication data, we can use this equation. Okay, this is a classical statistical equation to compute the half width of the confidence interval. All right, and this equation requires to know what is the variance. Okay, so you need to compute what is the variance of the across replication data. This equation requires to know like to have the number of replication. All right, this one is the t value. You can check this one in the t distribution table. Right, depends on the confidence level you choose. Alpha is the confidence level we choose. You want 95%, then alpha is 5%. All right, if you want 90% confidence level, then your alpha will be 10%. Okay, so check the t value in the t distribution table, and then we can compute h. Right, h is from the average to one end of the confidence interval. And if you want to know the exact value here, this is h, then you take the average. The average is the average of the across replication data plus the half width, then you will got the upper end. If you minus the half width, you will got the lower end. Okay, all right, so this is a summary of what we talked last time. Okay, the next question from this. Okay, and for either the tally statistic or the time persistent statistics, we still can use the same equation to estimate the average and the confidence interval. Yeah. Either whether it is either tally or time persistent statistic, you still can use the two equations to estimate the half width of the confidence interval. It applies for across replication data. Okay, but for within replication data, it will be different. Right. Now, the question I left to you in last week is how many replications we should run to have a good estimation of H. All right, so let's say we choose to give our estimation in the form of range rather just the average. We want to give a range. Then different people can predict different range, right? So, and if we look at the equation, we see that the half width here depends on the confidence level and the number of replication. Okay, so what is a good estimation of the confidence interval? What is a good estimation? Firstly, okay, so we take a very particular example here. All right, so let us look at the a cycle process of a certain product. All right, so let's say we start with our product, our final product here, and they are sold to the customer. Okay, and let's say for some time, some product is still working well, but some spoil because certain components in it down, fell. Okay, all right, and so let's say the factory is able to recollect the faulty product and then dismantle it for recycling. Okay, so we dismantle the faulty product, the faulty component we will throw away, right? And we use the still good one here. Okay, and so then we can sort it out, the components. All right, and then we can make the new recycle kits, the new recycle product. All right, and then sell it to the market. Right, so like different product may have different types of font, different types of value, okay, and the cost to recycle it may be different. Okay, in other words, the cost for recycling each product is a random variable. Okay, so let's say if we simulate this process and we want to look at the cost, the average cost for the recycling. All right, so we run our simulation a few times and we record the remanufacture unit cost each time. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have 20 replication here. And each replication, we come up with one remanufacture unit cost. All right, this is the average unit cost for the first replication. This is the average unit cost for the second replication and so on. So these are the across replication data. Okay, now we take the average of the across replication data from this 20 replication and we compute the variance from these 20 replication. Okay, and since the 20 replication data are independent, we will be able to calculate the confidence interval. This is the upper limit and the lower limits of our confidence interval. So basically, if we choose our confidence level 95% or our alpha is 5%, then our confidence interval will be range from 1.595 to 1.675. In other words, we are 95% sure that the mean of the cost is between 1.595 and 1.675. Okay, 95% confidence with this range. Is it a good estimation? Well, 95% confidence level is considered a quite high confidence level, right? When you say something and you are like almost 100% sure about it, is quite good, all right? So this 95% level confidence is considered quite good. Now, but we look at the range. This range of estimation, $1.595 to $1.675. Let's say, suppose that your boss is not happy with this estimation. Okay, the estimation range seems still not small enough for him. You want to narrow down this prediction, make it more precise. Okay, he asks you, are you able to make a more precise estimation, reduce this range or not? Okay, so basically here we are. If we plot the distribution of our remanufactured unit cost, all right, and you choose alpha 5%. So here would be 0.025. Here would be 0.025. And you tell your boss that I'm 95% confident that the average cost from 1.975 and 1.675. Okay, but if you want me to give you a more precise prediction, yes, I can do it. Okay, so all right, I can give you the estimate here. It is more narrow, more precise. All right, but with the lower confidence level. Okay, so let's say let's reduce it to increase alpha from 5%, now increase alpha to 20%. And so I can give you a more precise estimation, and the confidence level now is 80%. Alpha is 20%. Right, you see, the narrower the confidence interval, then the lower your confidence level, right? You see the error here would be smaller. Okay, the population will be smaller. That's natural. Okay, so you can compute with 80% level, confidence level, what is your confidence interval then? Okay, so okay, everything's still the same because we still keep the same number of replication here. So the average still the same, the variance still the same. Okay, but this is alpha is 5%, but if we choose alpha 20%, we will get, this is the t value. All right, and we got the new confidence interval. Right now we are able to shorten or narrow our confidence interval. Right, this is our first prediction Now we are able to increase its precision, right? Now we can predict that the mean of the cost is from 1.609 to 1.66. You see, it is narrower. This is good. However, we have to compromise with the confidence level. Before, we are confident with 95%, but now we are only 80% confidence. Like 80% of our observation is from 1.609 to 1.660. So this is not good. Right. So is there a way that we can achieve both high confidence level and small confidence quiz? Okay, we still want 95%, but we want this one. We want the precision in our estimation. Can we? How can we achieve both high confidence level and small confidence interval, narrow confidence interval? How can we do that, class? If we look at this graph, it seems that no way, right? If you want to narrow down this one, then automatically our level will drop. So what can we do here, class? How to have both high confidence level and small confidence interval? All right, we look at our formula again, okay? All right. Oh, I think we have an answer here. All right, one suggestion is increasing the number of replication. Very good, Anne. So let's look at the formula to confirm your answer. Right, this is our half width. We want small. Sorry, we want high, and we want small. Okay, so we want this half with small. Okay, so how high is high confidence level? Let's say we usually choose 95%. All right, we choose 95%. We fit this one, so this will be fixed. If we choose 95%, then we got T 95% here. Okay, and what we can do is to increase N. Yes, we can increase N here. Increase the number of replication here. And when we increase N here, this one will reduce. So that's right. Increase the number of replication, will have to reduce the half width of our confidence. Okay, so the question now is how much, to which extent we should increase our number of replication? We know that the more replication, the better now. We can give more precision prediction now, precise prediction now, but to how much? All right. Okay, so to how much depends on how much precise you want. Okay, so how much precise you want? Can you answer that question? Right, it will depend on the context. Okay, let's say okay, my computer is hang. Give it some time. Okay, how much precise we want. What is the precision that we decide? It depends on the context. For example, let's say the system you are simulating is a restaurant, and the output you are looking at is the waiting time of the customer. And normally, the waiting time the customer for that restaurant is about 45 minutes. All right. So the manager there expects that your simulation result regarding the waiting time of the customer should be your estimation from the simulation should be within 5 minutes. Okay, for example, if you tell the managers that from my simulation, the waiting time of the customer is very around 40 minutes plus and minus 20 minutes. Then this is unacceptable to the managers because your estimation is too wide. The average is 40 minutes and the variation, the prediction error may be plus or minus 20 minutes. It's very large compared to the mean here. All right, so he only allows you to have a precision about 5 minutes. Give me a prediction that the errors can be around 5 minutes only. And then I will accept it. All right. Let's say you are looking at the cost of increasing the resource or changing the layout, for example. All right, and you compare it with the money that you save. All right, and you say that on average you can save, from my simulation you can save about 1 million Vietnam dong, and with the error is 500,000 dong. That's a story quite big, and the manager may not accept it. Okay, 1 million dong, and the error is 500,000 dong, about 50% of the average. So he only allow you, please give me the estimation range with the precision plus or minus 100,000 dong only. Okay, then I if that information is helpful to me. All right. So in short, this echelon can be maybe 5 minutes or maybe 100,000 dong, any number. This is a practical value, right, from the user of the system. Okay, it depends on the context. It depends on the types of the output. Depends on the user requirement. Okay, so let's say we can obtain this information, right, outside. Right, we set the echelon. This is the design precision we need. The next step is we have to decide the number of replication we should run in our simulation in order to give our prediction that within this design precision, within this echelon. Okay, so we look at the Hartwig equation again. Okay, this is our Hartwig calculation. It should be smaller than this echelon. Okay, the Hartwig is equivalent to the error of our prediction. All right, we have the average and we plus and minus certain error. That is the half-width. Okay, so you can easily put it into how many replications you should run. All right, let's set this one equal to epsilon, then you would have R equal to T multiplied with the variance and divided by the epsilon that you want. Okay. Sorry, class. All right. Okay, so is it easy to do this? Right, we already have the equation to estimate the R here. Right, so what we need to know is the variance S, okay, the design precision epsilon, and the T value that you can identify the number of replication. Is it simple? Right. Is there any problem with using this equation, class? Can you see any problem from here, from this equation? Okay, let's look at this equation more carefully. All right, we want to know R, the number of replication. We need to know the T value. All right, firstly, we need to know this one. And look at the T value here. The T value here depends on the alpha we choose. Okay, so let's say choose alpha equal to 5%, it's okay. And it also depends on the degree of freedom because this is a T distribution. Okay, the T distribution have a degree of freedom. It is not like the normal distribution. We don't have any degree of freedom for normal distribution, but for T distribution, we have the degree of freedom. And the degree of freedom here is the number of replication minus 1. So what? We want to know R. And in order to know R, we need to know T. But in order to know T, we also need to know R, the number of replication. So we have a problem here, right? All right, and also look at the variance here, the S0 here. Okay, we want to know R. In order to know R, we need to calculate the variance. Now, how do we compute the variance? We need to run a few replication, right? And then we take the variance from the across replication data. So what? You also need to know how many replication you run, and then you calculate the variance. Okay, so again, we also have the problem here. We want to know R. And so we need to know S. But if in order to compute S, we need to know R. How many replication we run, and so we run and then we calculate S. All right, so we see that R not only appear on this side, but R also appear on this side as well. All right, so to solve this formula is not quite straightforward, right? So what should we do then? Okay, so this is the way we would do. Firstly, we don't know exactly how many replication we should run. So we just run a few times, a trial number first. Okay, so let's run a trial number first. All right, so from these initial runs, we will be able to calculate the variance from our across replication data. All right, so let's say we run 10 times first and see how. Right? And from the 10 replications, we are able to calculate the variance of these 10 replications. All right, so we start with the S0 first. All right, and we will use the value for our equation. Okay, and then for the t value, we know that the t distribution is very close to the normal distribution. Okay, actually, when you increase the size of the samples, then the t distribution will approach the normal distribution. Okay, so for the rough estimation at the beginning, we may want to use the normal distribution, the z distribution, instead of the t, because we want to avoid the trouble of the degree of freedom r. Okay, so first for the rough estimation, we will use the z distribution to avoid the trouble of identifying r, the r related in this formula. Okay, so we simplify this to this. Right, so we will got another number. From this equation, we will get one value of R1. All right, and this R1 will be different with the first one. Okay, and very sure that this R1 will be larger than the previous one. Okay, so when we have R1, we will try again. We will run the R1 times again. Let's say the first time we try with 10, and then for the new estimation, we get 15. Then we will run 15 times. All right, and then we brought into the equation again, and we will calculate the new R until we have the R very close together. All right, so let's take a specific example here. All right, we want to estimate resource utilization from the simulation. Okay, this is our output, resource utilization. And the design errors here is 0.04 or 4%. Okay, the resource utilization is in the percentage, right? Okay, so we want to estimate it within plus or minus 0.04. Our error criterion here would be 0.04. This is our epsilon. All right, with probability 95%. 95%. All right, so our confidence level here is 95%. Right, it's the same meaning with the probability 95%. Okay, so how should we do this? How many replications we should run in order to give an estimation of the resource utilization within plus minus 0.04 with a confidence level 95%. Right. So firstly, we run an initial sum runs first. Let's say we run 4 times first. Okay, so our R at the beginning is just 4. We run 4 times. We have 4 results. And we estimate the variance of these 4 results is 0.072. Okay, then we brought into this equation. Okay, the confidence level is 95%, so our alpha is 0.05, but because we look at the two tail here, so each one would be 0.025. So you need to look for the in the Z table, Z 0.025. Okay, and using this initial estimation of the variance. Okay, so the Z when alpha equal to 0.025 is 1.96. Okay, you take this one square, you will got this number. Okay, and this one is our error right children. Okay, we got 12.44. Okay, our R should be larger, equal than 12.44. All right, but we only run 4 times. And from our estimation here, we need to run 12.44 times at least. Okay, then what should we do? Okay, no, at least, but we are not so sure because this is just a rough estimation at the beginning. So we want to refine this number. Okay, so we will confirm this one by running more. Let's say we run 13 times. It's asked to run more than 12 times. We run 13 times and see how. Okay, when we run 13 times, okay, and we will, let's say this time we want to be more accurate. So we will use the t value, right? T value with the degree of freedom here. Okay, so R equal to 13, we look at the t distribution, looking for where alpha equal to 0.025 and the degree of freedom is 13 minus 1. We got this 2.18. All right, and we calculate the new one here. All right, and we got our new R. This is our new R. 15.39. Right, we start with 12. We start with we start with 13, and we end with R should be larger than 15. Okay, R should be larger than this number, larger equal to this number. So there's still a gap here. Okay, let's say if we try 14. Okay, the same here, we got the t, and we plug into this equation again, we got R still larger than 15, but it's quite close here. If we try 15, we got a new t value here, and we got a new R here, 14.83. Oh, they are very close here. All right, we start with 15 and we end up with another number, which is also very close to 15. So this almost the R that we need to find. Okay, 15 times. All right, so this is the way that it is like an iterative computation process. Okay, so we have to like try the error, try an error many times to come up with the R. Besides this way, you also can have a very quick estimation as well, right? Let's say we will try another way to have a quick estimation here. Okay, so let's say, okay, we look at our formula again. Okay, so we have, we use this equation. Right, so we see that different R will give us different H, right? All right, so firstly we run. All right, we will run a few times R first. All right, we still run the initial runs first, and we got the half width of this. All right, now what do we expect? We expect the half width should be smaller or equal to epsilon. So, okay, so we want the half width. This half width is equal to epsilon. All right, and it's also will be equal to t, let's say S1 divided by R1. Okay, we need to identify what is the replication that give me the half width equal to epsilon. Okay, now for simplification, we will assume that we will replace the t value with the z. Okay, so let's try replace t with z. Right, and we take the ratio of these two. All right, so we replace t with z just for approximation. This one will be cancelled with this one. And we assume that, let's say the variance doesn't change much. We assume that these two variants about the same. So we simplify it. Okay, so at the end, what do we have? We would have over H1 would be equal to R1 over R0. Okay, so we want to know R1, right? So put it again, R1 would be equal to R0 multiplied with 0H1 square. Right. In other words, this is the relationship between the number of replication and the half width. R1 over R0 equal to H0 over H1 square. All right, so the H0 would be our initial half width. Okay, from the initial run. The H1, let's set it equal to epsilon. This is the design precision we want. All right, so depends on how far we are from the design precision. Then we can identify what is our R1. Okay, this is just a rough estimation. And then we have to try slowly from here. Okay, we will back to our example, for example. Right, let's say we take this example again and using that method. Okay, we also run 4 times at the beginning. And then we look at the arena report. Okay, and we will get the half width from these 4 times. We don't have the report here, so can you quickly help to calculate what is the half width in this case? Can you help me to calculate what is our half width when we take for replication and we have this variance. Can you calculate it using the Z value? All right, I'm waiting for you to give me the number. The half width of the confidence interval when we run 4 times, assume that we got the variance of the for replication here, and we use the Z value 1.96. What do you get? Okay, I'm waiting for you to give me an answer here. Okay, you take H equal to UZ instead of T multiplied with S divided by square root of N. So what do you have here, class? Sorry, I don't have my calculator here. Do you have with you? 1.96 multiplied with 0.072 divided by square root of 4. How many do you get? Okay, thanks, Anne. We got 0.07. Okay, 0.07. All right, so this is the half width we obtained 0.07 for the resource utilization, but we want 0.04. All right, so 0.07, what we look at the ratio we have here, 0.07 over 0.04. Okay, here we are, and this is where we want to go. So the relationship with the replication. Okay, the R, and this is 4 times. So how many replication we need here? Okay, this is the replication we need for this precision 0.04. Okay, this is the replication 4 times, and we get this one. Okay, so can you tell me what is the number of replication here? Can you quickly calculate for me? Okay, I want you to calculate so that we can compare with the first method. Okay, thanks, Apple. Sorry, I don't know your real name. Okay, about 12.44. All right, so if we use this rough estimation, we will get, we should run about more than 12 times. All right, to have this ratio. All right, so in practice, you can have a quick estimation like this one, 12 times, and then you run slowly. From 12 times, you can 13 times, 14 times, 15 times, you try slowly until you get the half width is smaller than this one. All right, so in short, we start with a small number first, and then we have a quick calculation to see how far away we still need. All right, so let's say here we get 12.44. All right, we get this number, then we just slowly increase it. And then compare the half-width we get with this one. All right, so in Arena, it's easy. We run 13 times, you look at the report, you see the half-width. Oh, is it within 0.04 or not? It's still better than you try 4 times and then you increase 5 times, 6 times, 7 times. You don't know, but you jump from 4 times to 13 times. That's quite a big step. All right, and you know when you try the 13 times, 12.44 means 13 times. You already know that you are very close to the required number here, and from this 30 times you can increase the replication slowly. Okay, of course, when we run the simulation, it is very fast, so you can like give like if it's not time consuming to run it 20 times, and you try 20 times and you see it's already within the desired error, then it's okay, let it be. Okay, so what we say here is in the case where the simulation takes a long time to run for each replication, so we need to have a wise estimation to start with. All right. Any question in for this one class? Do you have any question here? Any question for this slide? Okay, if not, just try a few more slides, then we take a break. All right, give me some time. My computer seems hang again. Oh, no, it's go too far. All right, here we are. Okay, let's talk a little bit about the steady state simulation, right, before we take a break. Okay, so for terminating simulation, remember the number of replication is crucial for us to give a design estimation, a good estimation of the output. The number of replication is very crucial. Now for steady state simulation, let's recall when we need the steady state simulation. And if we want to run the steady state simulation, how should we set up our simulation? Okay, so the setup is like the warm-up time, the replication length, how many replication is similar to the terminating one. Okay, and then we go to the output analysis of the steady state simulation. All right. So you still remember what is the difference between a steady state simulation and a terminating simulation? Right. So for the steady state simulation and let's look at the simulation length. Which one is longer? The simulation length. The steady state simulation will be longer, or the terminating simulation is longer? The time we run the simulation, which one is longer? The steady state is longer. That's right. Right. Both of the simulation, we have to stop at some time. Right. Even though the system itself like may never stop, like the airport or a website. All right, the other website, it may never stop. It runs continuously, but we still have to define the simulation stopping time in any system we want to simulate. But for steady state simulation, the time we run would be longer than the terminating simulation. Okay, why? It is longer. Why we said it's longer? All right, we want to run the simulation very long in a steady state simulation because we want to evaluate the performance of the system in the steady state. All right, so let's look at the hospital, for example. Okay, if we look at the hospital in the early morning, you may see that the patient no need to wait for so long, very fast, because there's only a few patients there. All right, so but after a while, or let's say around like 10 o'clock, about 9:30 to 10, the hospital become in a steady state. Means that like any patients arrive around that time slot almost have to wait around an hour. Okay. So it's the performance output seem to be stable when the system already in the steady state. Okay, or let's say we look at the inventory level of a production line. It may fluctuate a lot at the first day of the week, but throughout the week, in the middle of the week, when the production line is already stable, then the inventory level are very stable. And let's say we want to evaluate our system when it is stable, not when it is fluctuate. Okay, and that's the reason we need to run our simulation long enough to allow the system in a stable state or steady state. All right, and we can evaluate its performance in that state. All right, so the question is, how long we should allow our system in a stable state so that it reaches the stable state? We have no idea, right? Right, so what should we do? How to decide the time for the simulation? Right, let's say for the terminating simulation, it doesn't matter, right? You just want to simulate the system from certain hour to other hour, like the restaurant from the morning to the evening when it closed. You want to observe the system change throughout the day. All right, or you just want to look at the system in a certain peak hour. So it doesn't matter it is steady or not. Right? But now we have to decide. All right, so so let's look at how we decide, how we set up our simulation, and so that we are able to get the steady state performance of the system. Okay. Right, like 1 minute for me to move from one slide to another slide because my computer is too slow. Sorry. Okay. It's so slow. All right, here we are. Okay. Now it's become too small. I'm not sure it's better in this way. Okay, never mind. All right, so as I told you, we want to evaluate our system performance in a steady state. And we have to look at certain parameters to know that whether the system in the steady state or not. All right. Okay. So assume that there are two ways for to look at here. Okay, let's say the output that we want to look at is the waiting time, for example. And we know that the waiting time at the beginning is very fast. Okay, almost zero. This is the time we run the simulation, and then it fluctuates. Okay, sometimes it becomes stable. And we want to look at this stable period here. All right, we don't want to look at this period. Okay, right, we don't want this. Right, the first method is that we will start our simulation from here. Okay, when we start our simulation from here, not from here, okay? Start from here. Means we start the simulation with a condition that the system already stable. So our job is we need to go to the real system and see the conditions of a stable system, right? In the real case. So let's say you go to the factory and you find out when the factory is in a stable state, what is the initial inventory level, or if it is the hospital or the restaurant when it is in a stable state, how many customers usually already in the system. Okay, so we have to set certain initial condition. We start the system from T0, but this T0 is when the system already reached the steady state, and you have to define the condition, the initial condition of that steady state. Like what is the inventory level already there? Some customer already in the system at that time and so on. And then from there, we run our simulation. Okay, so this is the first method, method one. We collect the data on the existing system to describe its initial condition. Okay, so we will initialize the simulation in a state that is representative of long-run conditions. That's what this sentence means. Now, the second way to initialize our simulation to a steady state is just to run it like normal, like the terminating one. Okay, we will start the simulation from here. All right, this will be our T0. All right, and then we will run the system for some times. While we run, we will monitor certain output. All right, certain output. All right, let's say we monitor the waiting time. And we will observe the plot. Okay, we will put it on the plot, see how these variable change with time, and from the plot using our eye power. All right, to decide when it is stable. Right, so after the first triome, after we just run it and we plot the data, we run it and using our eyeball to detect the state. All right, and then we can identify two phases of our simulation. The first phase we call initialization phase. Okay, it is here. This is initialization phase. All right, and the second one is the data collection phase. So what does it mean is that we will tell the software that there's certain initialization phase from time equal to 0 to t0 and do not collect any data in this phase. It's just for initialization, okay? And start to collect the data in the data collection phase. Start to collect the data from here onward. Okay. So in ARENA, do you still remember the word they use in the setup, in the run setup for the initialization phase? When you go to ARENA, you set up for the run. Okay. There's a word, it asks you to put warm up, excellent. Okay. There's one box that we usually ignore it, called warm up. Okay, so the warm up one is the initialization phase. When we put the value of the warm up time there, ARENA will understand that it will not collect any data for computation in that warm up period and just start to collect the data after that. So all of the results we get from the report is computed from the data in the data collection phase. And we already exclude the data from the warm-up phase. All right. So the next question would be, okay, how to do it in ARENA. We show it later. Okay, and also, all right, for practical purpose, is good enough after we identify the warm-up time and the rest, we would leave for the software to compute for us. But because it's theory lesson, so we will learn what should we, how should we calculate our statistic for this case. All right. All right, we take a break, class. We take a 15 minutes break. Okay, we'll back. Now my clock is 2:40, so we will back around 3. Okay, around 3, 5 to 3. Right. 2:55. All right, take a break, class.
Recording stopped.
Okay, now let's see in theory how we identify the steady state. Firstly, we have to identify the output, right? That by a variable of a system state variable. So that by looking at the system state variable, we can determine whether our system is already steady or not. Okay, so let's say that system state variable is y. Okay, it's y. Right, and now let's say this one this system state variable, let's say it is a cycle time. Okay, the cycle time. The cycle time of our product in a certain production system. Okay, so each entity, each product enter into the production line will have different cycle time. Okay, because the random processing time, random arrival time, so on. Okay, so here's what it look like. Okay, let's say we have the first replication. This is the number of replication. And then for the first entity or the first product, we observe the cycle time, first replication, first product, and then the second product of the first replication, and so on. Okay, so you end up with 1 and 1. Okay, let's say we have N1 entities in the first replication. Okay, and so on for the second replication and R replications. Right. So normally this is what we usually take, right? We take the average of each replication. Okay, we will take the average of the first replication. We will take the average of the second replication and so on, and then we will take the across data, right? All right. Now, because our purpose here is to identify the state, which means we want to see how the cycle time here change with time across the replication. So in this case, I will look at the average cycle time for each entity. Okay, so it will be like this one. I will look at the average cycle time of the first entity that enter my system through our R replication. All right, I take the average in this way. So this one, I will put it as y dot 1. Okay, so this is the average of the cycle time, the first entity through our R replication. Okay, and so on, and we have the average cycle time of the second entity. And in general, I would have the average of J entity in the system. All right, so this so-called average, I call it ensemble average. Okay, this way I call this one ensemble average. The average across replication for a certain batch, a certain product, a certain entity. Right, and now I will plot the ensemble average over the time. Okay, so this one I will plot this one versus time. Okay, so the plot that you see here in this slide is the plot of the ensemble average. You see, this is a simulation time. Okay, And each dot here on the plot is the ensemble average of each entity in this example, right? And from here, we will identify where is the warm-up time and where is the data collection time. Okay, so let's say we are able to look at this. Okay, we can say, all right, we will eliminate, we will exclude the data here. You consider this one warm-up, and we will start to collect data from here. All right, so for the first run, we will try to get the data to plot the ensemble average. Okay, and then from the plot, we will identify the warm-up time for the next run, for the real run. All right, now the purpose of this plotting ensemble average is for us to easily identify the steady state. How about if we plot like this one? You can plot like this one. You run one replication only, and we will plot like this. Let's say if we run one replication and we plot like this one, is it okay? It's still okay. And then you have the second replication and you have another plot for the second replication. Is it okay? Yeah, it's still okay. But in this case, it will be more difficult to detect the steady state because our data will be fluctuate a lot. Okay, so you will observe like many replication. For many replication, you observe a lot of plot, and because the fluctuation here will make us very difficult to detect when it reaches the steady state. Okay, so if the plot is smooth, then it's easier for us to distinguish the warm-up time and the stable time. Okay, now another way to smooth the plot for this purpose is to using the moving average. Okay, this is the moving average. This is the moving average formula. Right, you know the idea of moving average, right? The moving average like this one. For example, we take m equal to 1. Okay, m equal to 1. Then this formula becomes y dot j, the average of y dot j, this one, okay, would be equal to 1 over 3. All right, m equal to 1, it would be 1 over 3. And this is the average of 3 values. Y dot I will run from j minus 1 to j plus 1. So it would be j minus 1 plus yj plus y dot j plus 1. Okay, if m equal to 1. So basically, this is what we plot. We will plot the average of y1, y dot 1, y dot 2, y dot 3. And the next one would be the average of y dot 1, 2, y dot 1, 3, and y dot 1, 4. Okay, and the next one would be y dot 3, y dot 3, y dot 4, y dot 5. Right. The average, we take the average of 3 and it keep moving like that. If m equal to 2, we will take the average of 5 and then moving like that. So this is the way to get a even smoother plot and easier to identify the state or system. Okay, so again, the main point here, the method here is to use the ensemble average, either the normal way or the moving average to get the plot and plot the value of the ensemble average over time. Okay, I will show you how to do that in the arena later. But let's say after we already identify the warm-up time and the steady time by this way, how we will proceed next. All right. So again, the idea is simple. We need to remove all the data during the warm-up period and our analysis just based on the data in the steady state period. So let's say in the first replication, is it too small? Right, the screen is bigger, but it's slower. Okay, so let's say for the first replication, this is all the data we get during the simulation time, but we would delete or truncate, cut off the data during the warm-up time. All right, so our data is we put the abbreviations like this one, right? The average, this is the average of the first replication without the data from the warm-up time. Okay, so when we take the average, we just take the average of this one. And similarly for other replication, we remove this one. Okay, and we still need more than one time running, means we still need certain number of replication in this case. And we apply the normal way of output analysis just as the terminating simulation. Okay, so again, the replication method for steady state simulation is that we will remove, we still run our simulation a couple of times, many replications, but each replication we will remove the data during the warm-up period and just use the data in the steady state for analysis. All right, the other formula like the average, we need the average from the across replication, and we also calculate the half width from the across replication data as usual. All right. Okay, so this one we call truncated replication. Still need to repeat many times, but remove the data in the warm-up period. Okay, so this is the formula we use for estimating the average. Right, after removing the warm-up data, okay, this is the average across replication. We have R replication, we take the average of R replication, and this is a confidence interval. All right, everything just like the terminating one. Okay, and even though you can identify the warm-up time using the plot like that one, sometimes it's also difficult to detect by our eyes. So a rough rule here is that if you have n observations for one replication, All right, and you want to delete the observation for the warm-up periods, then the number of that you delete, all right, should be smaller than this value. Okay, n minus the numbers that you delete should be smaller than this number. And this is just a rough rule. Okay, or let's say if you look at the time, right? T is the time that we want to collect our data, and T0 is the warm-up time. And TE should be roughly larger than 10 times the warm-up time. Okay, this is just a rough rule here. Okay, skip. We will go back to this one again. All right, now that is the truncated replication method. But remember that for state simulation, we have to run the simulation much longer than the terminating simulation, right? And then we still need to repeat that run many times. We need to have replications and then treat it as like the terminating. That sometimes is difficult because it's already long, its replication already long, and then we have to repeat many times. So each time the simulation have to go through the warm-up. It takes a lot of time, and then it just collect the data from the each step. You can imagine it's quite time consuming, right? And it's especially difficult when it is hard for us to identify the warm-up time because the warm-up time is too long. All right, it's too long and it's hard to detect where it is. All right, in that case, we can resort to another method we call batching single run. Okay, batching single run. So in this method, we don't run so many replications, one time only, but this one time run is really, really long. All right, so like in the truncated replication, let's say we want to run 10 times. And each time 5 days. If 5 days is considered long enough for the system to be stable, all right, and we run 10 times. We use this one for truncated. All right, now for batching single runs, we can run it one time, but 50 days. Okay, so the second one will have the advantage that we only need to go through one time to eliminate the warm-up time, and then the usable data will be a lot for the 50 days. Okay, so let's say if we identify the warm-up times is 2 days, then for the truncated situation, like each replication, we have to eliminate the data for the first 2 days, and then we only have the data of the 3 days, of the rest 3 days, right? And then we repeat like that 10 times. But for the batching single run, we run 50 days, and our warm-up time is 2 days. So we have the data for 48 days. That's a lot compared to the first one. That is an advantage. All right, but we have a statistical problem in this case. You know what is the problem? Remember the reason we have to run many replications? Do you still remember the reason? We want independent data, right? You want independent data from different replications so that you can use the classical statistical equation to estimate the half width of the confidence interval. Remember that? I'm keep saying that. Okay. The same thing here. If we use a truncated replication, it's 5. Let's say here we have 10 replication, and the 10 replication results are independent. So I can estimate the half width of my confidence interval using the equation that we learned. But here, if we run only one time, even though very long one, the data here would be dependent. Okay, all the data during the 50 days are dependent, and so we cannot use the normal calculation for our estimation. Okay, so the problem for the Bayesian single run here is the correlation among the data within one run. All right, so what should we do? Okay, there's a technique here. Right, the technique is like this. All right, let's say we run a very long run for 50 days, 0 to 50 days, and there's a lot of data here. All the data here are dependent. But we will prove that if we break the run into large batch, or we group our data into large batch, like this, we group our data into batches. Okay, this is batch 1, batch, okay, batch 2, batch 3, and batch 4, so on. Okay, and if the batch size, this one is big enough, then the batch tend to be independent from one another. Okay, if the batch size is big enough, then they tend to be independent. All right, so the technique here would be breaking the run into a few large batches. Okay, and then we will treat each batch here as a replication. Let's say you divide into 5 batches, then you have 5 replications. All right. So for the batch, that is the name. This is the reason why we give it this method the name Bayesian single run. Okay. So you may wonder, like, how large is large, and then how many batches we need. Does it matter or not? Right, like there's the number of batches also matter in this case. Like the number of batches will be equivalent to the number of replications in this case. So does it matter? All right, we will not go into details for this one, but I will tell you what happened in ARENA. All right, so if in ARENA you choose single replication, you choose single replication, and you also tell about the replication length. ARENA is still able to calculate the half width in the report using the batching method. Okay, it will use this batching method for single replication. So it will batch the data, certify this condition if it is a tally statistic. All right, so it will pass so that each group of the data have at least 320 observations if it is tally statistic. For example, the waiting time of the customer, then the batching should be large enough so that each batch would have at least 320 customer, waiting time of 320 customer. All right. Or if it is the time persistence statistic, then the condition in arena is that equibus, so that at least 5 units of simulation time would have at least 300 changes in the level of discrete change variable. All right, so it will automatically form the number of batches that satisfy this condition. And as our simulation proceed along the way, it will increase the number of batch. Okay, so at the end, when the simulation finish, it will try different ways and will end up usually about from 20 to 40 batches. Okay, why not lesser than this? Why not more than this? Right? Because people already study that lesser than this or more than this would not help in a statistical point of view. Okay, the result doesn't change significantly. All right, and if you treat the batches that it divide from that single run as the number of replication, all right, if you test the correlation between the batch, all right, and then calculate first the half width from that one. All right, now what happened if our simulation length isn't long enough to divide into big batches and to sufficient number of batches? You will read in the report. In the report, you will see that in the report, the column half width, you will see insufficient. So when you read the insufficient, you see the insufficient half width in the report, you know that it's because your simulation length is not long enough for ARENA to apply the half width calculation. Okay, the half width calculation require you to have sufficient number of data, and those data need to be independent. Right. So instead, just blindly using the half width calculation, it tells us that the data is insufficient for that calculation, and you cannot obtain the data. All right. Okay. Similarly, if you run the replication, so few replication, you may also get a report insufficient half width because you don't have enough samples. All right, so anyway, you just need to understand how it's gone in ARENA. You no need to do this one by yourself. All right, the one that you really need practically is to identify the warm-up time. Right, so now I'm going to show you how to identify the warm-up time in ARENA. Okay, I'm going to share with you the ARENA screen. You can read the information on the slide, but I want to show you directly from ARENA. Okay. Let me open a model that we already tried in our lab. Let me open ARENA. Okay, here we are. Right, I'm opening this one. Mm, right, did you do this example in the lab? Okay, the manufacturing system, and you learn the entity transfer. You have different parts enter the manufacturing system, and each visit different cells, each have different rules. Okay, we take this example. Let's say we are interested in the inventory level of this system. Okay, and when we want to look at the inventory, we usually need to look at the inventory when the system at the steady state. In other words, we need to run the simulation long enough when the inventory level is kind of stable. We want to look at the average inventory. All right. So, of course, we don't know. At the beginning, we don't know when the system will reach that steady state. So we need to obtain the data. And in this case, it's the data of the inventory level. All right. And then we will plot it. And then we will decide the warm-up time from the plot. Okay. So how do we record the inventory level? Right. The inventory in a manufacturing context actually means the number in the system, right? The number of entity in the system is the inventory in a production line, right? So how do you record the inventory then? Is it available in Arena default report? Number in system, the average number in system. So we don't have that in the default report. Okay, in the default report, we have the number entity in, enter, and then the number out, but we don't have the average inside the system. Okay, so one technique that we learned before the midterm is to create our own variable to record the number in system. So whenever an entity enter the system, we +1, and whenever it's out of system, we -1 for that variable. All right, that's what one technique we learned. All right, but we also have Arena default variable to record that one, okay? And I will ask Arena to record that information. And in order to have that information in the report, we need to use the statistic data model. Okay, so let's go to statistic data model. Here we are. Okay, and let's name the statistic total WIP, work in progress. And number in the system will be time persistent. Time persistent, it change with time, so it's time persistent. All right, I will use the default expression in Arena, entity WIP. Entity WIP, it will tell us about the number of entity in the system. And in the bracket is the type of the entity. So in this example, we have 3 entity types, part 1, part 2, and part 3. So I will ask Arena to record the entities WIP of part 1, part 2, part 3. Okay, this formula, this expression is ARENA default. You can utilize this one. All right, so okay, and we want it to appear in our report under the label of total WIP, and we will collect the home period. All right, now if we ignore this one, what we have is the total WIP in the report, and what it shows would be the maximum, the minimum, and the average. And the average would be the time persistent. It will calculate the time weighted mean for us. All right, and then also calculate the half width. All right, if we set up, let's say we set 10 duplication in 5 days. All right, and we don't know the warm-up period yet, so just leave it 0. However, remember that we need more than that. We need more than the summary statistic, like the average, the confidence interval, the maximum, minimum. We want the WIP data record throughout the simulation, throughout the 5 days here, and for the 10 duplication here. Okay, so all right. So in this case, I will need this one, the output file. All right, so in this output file, I will type in the name that I want ARENA to save the total WIP data into that file, the name of the file. All right, and later after I finish the simulation, I will open that data file and then I will plot from that data file. All right, so how to put this one? You just double click in it. You can press this one to choose the location of the folder you want to store. All right, and then type in the name of the file, right? Just any name that's meaningful to you, and the extension should be .dat. Okay, pay attention to the extension here. It's .dat, .dat. Right. So after we run this one, we will get a total WIP history.dat, and we will use the an application ARENA to plot this one. Okay, so let's run it. We'll run this one for 10 duplication, each duplication 5 days. Okay. 10 duplication, 5 days, no warm up. Okay, let's run it. And for this purpose, to make it faster, remember in the run control, you choose batch run. Right? It will be faster. If you don't choose batch run, it will go through animation. It will take a lot of time. Okay, use batch run. We use animation when we want to verify the logic. But let's say the logic is okay. Now we just want the result and use batch run. No animation here. Okay, then we can have a quick result. Okay, monitor here, we are 10 duplication, 7 duplication, 8, 9, 10. Okay. All right, let's see the results. Okay, in the category overview, we can look at the total WIP. They summarize the total WIP. This is the average from 10 duplications. This is the half width of the confidence. Right, we have the minimum and maximum, right, so on. Okay, if you want to look at the result for each duplication, then you can go to the user specifier here. All right, and it will give us the result for each duplication here. replication 1, replication 10, replication 2, and so on. We have 10 replication, but we need more than this. So this time we use the total width dot dat, that. Right. In order to open that file, we will need to an application from an Arena. It is Output Analyzer. Okay, you need to go out from here. You cannot access this from here. Okay, if you are still in Arena window, if you look at the tool, you see there's only Input Analyzer, the one that we use to fit the distribution to our data. All right, and the Process Analyzer, I will tell you about this one in the next class. But for this purpose, we need to use Output Analyzer. It's not here. You have to open it another way. All right. So we go to the program files, the folder where we install Arena. For my case, it is in C, in this C, program files. And look for Arena, Rockwell software. And Arena. Okay, now you look for the Output Analyzer .exe. Right. Oh, I'm sorry, you cannot see it. I forget to share with you. Okay, let me do it again. Let me share the screen and do it again. Okay, let me do it again. All right, I'm going to this C. Okay, go to program files and look for Rockwell software. And then Arena. Okay, and then we look for the Output Analyzer .exe. We have input.exe here. This one is the input analyzer, but let's look for the output. It's the output one. Yeah, here we are. Okay, output.exe. Okay, now double click on it. All right, so this is the output analyzer. Right, you can open the data file, the dot file in this output analyzer. All right, so let's plot that data. Right, you go to graph. Go to graph and then plot, and then choose the data file you want to plot. So I will add the data file here. Just now I put it in this one, in this folder. The name of it is total width history.dat. Open it. All right, so if we choose to plot the first purification, we choose purification 1, for example. Then we will see this. Right, we can see that, wow, there's something here. Or it seems to be, well, maybe this one probably is the warm-up period, maybe. Okay, around this, let's look at the second replication. Okay, we choose the same file. Okay, let's choose the second replication to see how. Okay, the second replication seems like, well, we don't know. It's quite arbitrary here. It's quite subjective here. But let's say if we, right, let's say if we also eliminate like this one, what happened? All right. Well, it's quite subjective, right? Let's say if we look at the 10 replication together. Choose all. Well, here we have. All right. Now, can you use your eye power to detect the steady time? Can you see it? Frankly speaking, it's very hard for me as well. But this is an example I get from the textbook. And it say that, well, from this chart, we can see that is around this time, 2000 minutes, around 2 days. All right, we can take the warm up about 2 days here. To me, it's quite subjective. All right, but I don't know. Well, it's hard really case, but this is the common way that people usually do to detect the warm up time. There's many other methods. If we read in the literature review, many publications will suggest different ways to detect the warm up time. But this is the most simple way for us to do. Okay. How about the ensemble average? The ensemble average that we learned in the theory. All right, so I'm not sure it's the correct way or not, but this is what I found in Arena. You can put this plot using the ensemble average. It's like this one. All right, we plot the average of this one like this one. All right, but you have to batch the data. Right, it doesn't, the Arena doesn't allow us to plot the average for each entity like this one. It's a lot of data. We have to firstly batch this one. I batch it first, and then we will take the ensemble for the batch. Right, so let's say for the first replication, you group into 20 batches. The second replication, you also group it into 20 batches. All right, and then we do the ensemble average for the first pass, second pass, third pass, and so on. All right, so if you want to do that, you can try this one at home. And firstly, you have to batch it, analyze, batch. Okay, and I will use the data, the history, total WIP history again. All right, and you ask it to batch all the replications. Okay, the batch here will be in time. Okay, it's time. Just now we run for 5 days, right? 5 days. 5 days means each day is 60 minutes. So we would have, 5 days, each day is 24 hours and each hour was 60 minutes. So we will come up with about 7,200 minutes. Right, so if we divide it into 20, let's say 20 batch, then each batch would be around 360 minutes. Right, so 360 minutes. So let's put the size of the batch is 320 minutes. And we need to save the batch means the means of each batch in a certain file. All right, so I will save it in, I already saved it at home. I try to save it again here. Oh, no, this one is not good. All right, I will put it in name here. I put modem 72 batch 300 minutes. And the extension for this file is FLT. Okay, so all right. All right, so after I create the batching file, now I can plot the ensemble average. I can plot it here. All right, I will remove this one and okay, as a new one. This time I have to use the FLT. All right, this is the name, the file that I just created, past 320 minutes. All right, so it's going to look like this one. It's smoother and much smoother and easy for us, right, to choose this one as our well, some of our right warm-up time, right? We can choose this here. All right, we don't know, but you can try, okay? I think here would be safer. I think here would be safer. It's around 2 days if we choose here. Okay, or you can plot the moving average using this one. The moving average, the same here. Choose the file that just created. Where is it? It should be FLT. Okay, you can open this one and plot the moving average. All right, for the moving average, because I forget to choose the condition for the moving average, but it's the plot even smoother. Or you can have a look at your data as well by using the table. Okay, have a look at the data that we just created. Okay, let's browse this again. All right, let me open it again. All right, now let's look at the table. Okay, this is the result from the batching. Okay, so this is the ACEs. This is the time, the simulation time that it took. In total, you would have 20 batches. Each batch around 320 minutes. Okay, and this is the average for each part. This represent for the each part will be equivalent to one replication. All right. Okay, so I hope that it will be helpful for your project. Okay. Right, do you have any question here? Any question, class? Is next week our last class of the course? Tuần tới có phải là tuần cuối cùng của tụi mình không em? Các bạn nào có tính không? Có tính thời gian không? Phải tuần tới là tuần cuối cùng của tụi mình không? No idea luôn. Nếu cô nhớ không lầm thì tuần tới sẽ là tuần cuối cùng của mình ha. Các bạn trả lời. Sau đó còn một tuần make up. Ok. Hy vọng là tuần sau là mình sẽ xong ha. Ở lớp mình có bị nghỉ lễ bữa nào không ta? Tuần sau thì mình sẽ còn một bài nữa là bài comparison ha, giữa các design khác nhau. Rồi. Và tuần sau là mình sẽ có một cái lớp lab online ha. Tuần sau sẽ có lớp lab online và lớp theory cũng online luôn, và mình thi cũng sẽ là online luôn. Rồi đề thi như thế nào thì thầy cô đang suy nghĩ, nhưng mà sẽ là thi online. Ok ha tụi em ha. Còn project thì mình sẽ không có presentation, mà mình sẽ nộp vào cái tuần cuối cùng của cái tuần thi final. Thường là mình thi final 2 tuần đúng không? Thì cái chủ nhật cuối cùng của cái tuần thứ 2 là sẽ là hạn chót để tụi em nộp ha. Tụi em nộp project của mình. Rồi, để cô sẽ post cái đó lên Blackboard cho nó official. Rồi, tụi em có câu hỏi gì không? Không thì mình ngưng tại đây. Rồi, ok, cô có record, cô sẽ up lên ngay. Rồi, không có câu hỏi gì không tụi em? Ok, vậy thì mình stop ở đây ha. Rồi.
Recording stopped.
Ok.